Many devices use a combination of electric and magnetic fields to control the motion of charged particles. Electric fields, we know, can speed charged particles up and slow them down. And magnetic fields, while they do no work, they can steer the particles, change their direction of motion. So between these two, between your sort of accelerator and brake here and your steering here, we can attain very fine control over the motion of individual electrons or other charged particles. So, okay, a common such device in a laboratory setting is a mass spectrometer, which is used to determine the chemical composition of some unknown sample. So here's a simple schematic of what the device might involve. We start with some sample of material, some substance down here whose identity we're trying to determine. We heat it up enough to chemically separate it, ionize some of the component molecules, and let those positive ions drift in through a small hole in this plate into the space between these two plates. This is a parallel plate capacitor. So we've got an EMF generating a uniform electric field between these two plates. And the purpose of this component is to accelerate those ions, to speed them up as they move from the bottom plate, passing in through this small hole, initially with a very low speed, then accelerated them, speeding them up to some known final speed as they exit through the top plate here through this small hole. So here come our ions speeding up across that gap. Then after passing through our accelerator here, they enter this region with some knowable speed. And upon entering this region where there's a uniform magnetic field out of the page, they're going to feel magnetic forces. So coming in, they're going to feel a V cross B out of the page, so a magnetic force initially to the right, and that's going to curve their path, and we'll get that uniform circular motion as long as they remain in this region. So particles coming through this region with different masses, so different charges, exiting the plates with different momenta will follow circular paths with different radii of curvature. This is the gyro radius here, RG for that particular path, gyro radius there, RG. So these different curved paths have different gyro radii. And that could be measurable by your device. Your device could have some sort of screen over here that records where your particles impact, then thereby determining the gyro radius of their path. And from that, we'll be able to back out this mass to charge ratio. Okay, so let's just look at a few calculations. Starting here with the parallel plate capacitor part, if our ions start very nearly at rest as they drift in through that small hole, then are accelerated across the plates, we can use conservation of energy to show how the electric potential energy the ions have at this plate is converted into kinetic energy by the time they reach that plate. So delta U plus delta K is 0. So that implies that the kinetic energy gained by our ions is the opposite of the change in potential energy, which is the opposite of Q, the charge of our ions, times the potential difference that they move through as they go from this plate to this plate. Well, here's our high potential plate. Here's our low potential plate based on the orientation of our battery here. So the delta V that they're going through will just be the opposite of the EMF. They're going from high potential to low, so the delta V is negative here. So the change in kinetic energy, 1/2 mv squared, will be equal to the charge of each ion times the EMF that we're pushing it through here. Okay, so we can solve for our, let's just leave that as it is for the moment. And note also, once you enter the magnetic field region, this gyro radius, we've computed an expression for that previously. The gyro radius for some particle undergoing uniform circular motion inside the magnetic field depends on the momentum of that particle, mb, divided by its charge and the B field strength. We've derived that before. So let's use this to replace V here in terms of these variables. So this here says that the speed of the particle could be represented as QB times the gyro radius divided by m, and there's that charge to mass ratio showing up right there. Let's sub that in for our speed right here. So we get 1/2 m v squared will be q over m, charge over mass squared, times b squared rg squared, and that equals q times the EMF. Lastly, what we're trying to solve for here is that mass to charge ratio, which we can get by just rearranging this expression. Let's see, I'll multiply both sides by that mass to charge ratio, and let's see, it's going to come out to be, I'll skip a few steps of the algebra here. It's going to come out to be the field strength squared divided by 2 times the EMF times the gyro radius squared. So the value of this result is that if in our device we have a known magnetic field, a known EMF, and we're able to measure the gyro radii of these different paths based on recording where these particles impact on some fluorescent screen over here. So we're able to measure this, then we can determine the mass to charge ratio of each particle. So if our sample is composite here and containing a number of different compounds or different components, all with different mass to charge ratios, we'll record how many of each kind impact at these different radii, and we'll get the spectrum of all the masses of all the different components in our unknown sample here. And we'll be able to do a bit of detective work to back out, based on that collection of mass to charge ratios, what those components, what the chemical composition of our sample might have been.